In the spring of 2024, a Photonic AI chip running a standard inference benchmark posted an energy efficiency figure of more than 1,000 trillion operations per watt. Let me tell you what that actually means in plain English. The best electronic GPU available today, the kind running inside every major AI data center on the planet, manages roughly 1 to 4 trillion operations per watt under real workload conditions. You heard that right. This chip was not 10% more efficient. It was not twice as efficient. It was operating in a different category of physics entirely. And the efficiency number is not even the real story. The real story is what happens to the heat. And if that question is already forming in your mind, hit a quick like and subscribe, because by the end of this video you are going to understand exactly why the thermal ceiling that every AI chip roadmap on the planet is built around is not a law of physics. It is a consequence of using the wrong material. Every computer chip in the world runs on the same basic transaction. You apply a voltage, a transistor switches, a calculation happens, and a small amount of energy bleeds out as heat. At the scale of a single transistor, that heat is immeasurable. At the scale of a modern AI accelerator, which contains more than 80 billion transistors, all switching billions of times per second. It is the dominant engineering constraint on the entire industry. Here is the detail that puts everything into perspective. The heat produced by an AI chip is not a side effect of poor design. It is a direct mathematical consequence of moving electrons through resistive material. Every switch dissipates a fraction of its switching energy as thermal output. Shrink the transistor, and you fit more on the same die. More transistors switching at the same frequency means more heat per square inch. The physics does not negotiate. TSMC's most advanced production nodes generate thermal densities exceeding 100 watts per square centimeter under full AI workload conditions. To give that a reference, you can picture a 3 nanometer AI chip under load is generating roughly 1/60th of the sun's surface output in a package the size of a postage stamp continuously. The International Energy Agency reported in 2023 that global data center cooling already consumes more than 200 terawatt-hours of electricity annually, comparable to the total power consumption of several mid-sized nations combined. Most people who follow AI hardware never encounter the crossover number. It is the point at which the energy required to cool a chip cluster begins to exceed the energy the cluster uses to compute. Lawrence Berkeley National Laboratory projects that for the densest inference deployments, that crossover is not a future scenario. It is already occurring in specific rack configurations today. The industry's answer has been dark silicon. When a processor cannot dissipate heat fast enough to run all of its transistors simultaneously, it powers sections of the chip off entirely, leaving functional compute area idle to keep the thermal envelope from destroying the package. On the most advanced AI chips currently in production, as much as 30% of available transistor area operates below rated frequency or stays powered down during sustained inference workloads. That is not a marginal inefficiency. That is a third of the chip you paid for, throttled by heat. They hit a version of this wall before. In 2004, Intel canceled its 4 GHz Pentium 4. Clock speeds, which had doubled every 2 years for 3 decades, stopped. The industry pivoted to multi-core, not because multi-core was faster per clock cycle, but because the thermal math on single-core scaling had broken. The same rethink is now underway at a deeper level of the stack. The thermal wall is not a projection. It is current infrastructure reality, already costing the industry hundreds of billions in cooling overhead, stranded compute, and energy spend. But one program looked at that wall and decided the right response was not a better cooling system. It was a different kind of physics. And what that program announced next was dismissed by most of the industry within 48 hours of publication. In 2022, a research team operating out of Tsinghua University published a result in the journal Nature that the photonics community had been working toward for nearly 2 decades. They demonstrated a photonic chip, a processor that used light instead of electrons to perform the core matrix operations at the heart of every modern neural network. The claimed performance figure was extraordinary. The claimed heat output was, for practical purposes, negligible. And the mainstream semiconductor press moved on within a news cycle. The objections were not unreasonable. Photonic computing had been a research promise since the 1980s. Every prior attempt had run into the same set of walls. Photonic components were too large to integrate at chip scale, too sensitive to manufacturing variation to yield reliably, and too difficult to interface with the electronic systems that fed them data. The consensus was polite but firm. Interesting physics, not a chip. Here's what most people get wrong about that dismissal. The objections were accurate descriptions of prior photonic architectures. They were not accurate descriptions of what the Tsinghua team had actually built. What the team demonstrated was not a standalone photonic processor intended to replace electronic logic entirely. It was a hybrid architecture, a photonic compute layer integrated directly onto a CMOS-compatible substrate, designed from the ground up to work alongside existing electronic components rather than replace them. The photonic layer handled matrix multiplication. The electronic layer handled everything else, and the manufacturing process was compatible with existing semiconductor fabrication infrastructure. The dismissal followed a pattern with a long history. In 1952, engineers building vacuum tube computers examined the first solid-state transistors and noted correctly that they were fragile, inconsistent in output, and nowhere near the performance density of the tubes they were meant to succeed. The manufacturing, they said, was not ready for serious work. We all know how that ended. What the Tsinghua result actually represented was the first time a photonic compute layer had been demonstrated inside a manufacturable architecture. Not a research bench, not a fiber optic testbed, but a chip-scale device built on processes that existing fabs could run. The IEEE Photonics Society flagged the paper as a significant fabrication milestone. Most general technology coverage missed that distinction entirely, but the skeptics were not entirely wrong. Photons have a problem that electrons do not, and it is a problem that the Tsinghua result had not yet solved. The mechanism that makes photonic computing fast is the same mechanism that makes it, at first reading, completely unsuitable for the job. Picture a glass prism sitting in a beam of white light. The moment the light enters the glass, it splits. Red bending one way, violet bending another, every frequency traveling its own path simultaneously, none of them interfering with the others, none of them generating heat. That is not a magic trick. That is the default behavior of photons moving through a transparent medium. And it is the physical property that makes photonic computing fundamentally different from anything built on electrons. Now here is the part that changes everything. The core mathematical operation inside every neural network, the operation that runs millions of times per second during inference, is matrix multiplication. You take a grid of numbers, multiply it against another grid of numbers, and sum the results. Do that fast enough, at large enough scale, and you get a language model, an image classifier, a recommendation engine. The computational cost of that operation is the reason AI chips exist as a distinct product category, and matrix multiplication maps onto optical interference with a precision that looks, from a certain angle, almost too convenient to be real. A Mach-Zehnder modulator, a component the size of a few hundred micrometers built from silicon waveguides, encodes a numerical value into the intensity of a beam of light. Send two encoded beams into an optical interference structure, and they combine according to the laws of wave superposition. The output intensity encodes the result of a multiplication. No switching, no resistive dissipation, no heat. The calculation happens at the speed of light, in the time it takes a photon to travel the length of the device. What passive photonic inference eliminates is not just warmth. Walk through the full list. Switching energy losses, gone. Dynamic heat generation, gone. Cooling overhead for the compute layer, gone. And dark silicon constraints. The throttled third of every advanced chip that exists solely to keep the package from destroying itself, eliminated at the architectural level, not managed around it. A 2023 paper in Nature Photonics, reporting on a photonic matrix multiplication accelerator, documented throughput efficiencies exceeding 100 trillion operations per watt on targeted inference tasks, against an H100 baseline operating at roughly 2 trillion operations per watt under comparable conditions. That is not a better chip. That is a different physics. But the photonic compute layer only handles the multiplication. It still needs data delivered to it and results read back out. That interface between the photonic core and the electronic memory feeding it is where the architecture nearly collapsed. Think about filling a fire hose from a garden tap. The hose can move thousands of gallons per minute. The tap delivers maybe 5. The bottleneck is not the hose. The bottleneck is everything upstream of it. That is the interface problem in photonic AI computing, stated in the plainest physical terms available. A photonic matrix multiply unit operates at speeds that modern DRAM cannot match. The memory bandwidth wall, the gap between how fast a processor can compute and how fast memory can deliver data to it, is already the primary performance limiter for electronic AI chips. For a photonic core operating at its native throughput, the gap is not narrower. It is wider by an order of magnitude. Here is the brutal catch. You can build a chip that computes faster than any electronic device in history, and if the memory interface cannot keep it fed, you have not solved anything. You have moved the bottleneck. The apparent contradiction is precise. A photonic inference chip that outperforms electronic GPUs by 200 times on ops per watt, but stalls waiting for data, delivers less useful work per second than the chip it was supposed to replace. The skeptics who raised this objection in 2022 were pointing at a real engineering problem. What they did not anticipate was the response. The solution was not to speed up the interface, it was to eliminate the need for it. Near-memory photonic integration places the photonic compute layer directly adjacent to analog memory arrays, not connected to them through a digital bus, but physically co-located on the same substrate, reading weight values optically rather than electrically. The digital serialization step, which is the source of the bandwidth wall, disappears from the critical path entirely. This is where the architecture becomes genuinely counterintuitive. Running inference in the analog domain means accepting a level of numerical precision that would be considered a defect in a digital system. Analog components drift. They introduce noise. For decades, that made analog compute unsuitable for serious numerical work. But transformer-based neural networks, the architecture underlying every major language model and vision system deployed at scale today, are remarkably tolerant of reduced numerical precision. The models were already being quantized to 8-bit and 4-bit integer representations to fit on smaller hardware. Analog noise in the photonic domain falls within the same tolerance window. It sounds like a flaw. It is the feature. A 2023 study from MIT's Research Laboratory of Electronics confirmed that photonic analog inference on a standard ImageNet classification benchmark achieved accuracy within 1% of full precision digital baselines. 1%. At a fraction of the energy cost. That result closed the interface objection. What remained was whether two mechanisms proven in isolation could be integrated into a single package that a semiconductor fab could actually produce. Building a photonic compute layer is one problem. Building an analog memory interface is a second problem. Integrating both into a single chip package on a manufacturing process that does not require a completely new kind of factory is a third problem of a different order entirely. Photonic components are built from silicon waveguides, optical modulators, and photodetectors. Electronic components are built from doped silicon transistors and metal interconnects. These two material systems have different deposition temperatures, different etch chemistries, and different tolerance windows for contamination. Running them on the same substrate, in the same fab, through the same process flow, is the kind of integration problem that has historically required a decade of process development before it yields reliably enough to sell. Here is what makes this genuinely extraordinary. The silicon photonics process, the specific manufacturing approach that places optical waveguides directly onto a CMOS substrate, had been in development at IBM Research and Intel since the early 2000s. By 2020, it was a qualified process at multiple foundries, including Global Foundries and TSMC's Silicon Photonics line. The photonic components and the electronic logic were already on compatible manufacturing platforms. What the Tsinghua architecture and subsequent commercial programs like Lightmatter's Passage chip exploited was not a new fabrication breakthrough. It was the maturation of an existing one. You can build this on the same fabs that already make every other chip in the world. That sentence is worth reading again slowly. The remaining integration challenge was calibration. Photonic components are sensitive to temperature in a way that electronic transistors are not. A waveguide tuned to route light at one wavelength at 20 degrees Celsius will route it differently at 30 degrees. In a data center environment where rack temperatures fluctuate continuously, that drift degrades compute accuracy in real time. The solution is an AI-assisted calibration layer. A lightweight electronic controller that monitors the optical output of each modulator and applies continuous micro-corrections. the way a noise-canceling headphone samples ambient sound and generates a canceling waveform faster than your ear can detect the interference. The photonic core never drifts outside its accuracy window because the calibration system never stops watching it. The part that rarely makes it into public reporting is what this calibration layer revealed during extended testing. The correction signals it generated were not random thermal noise. They followed predictable patterns tied to workload type, meaning the calibration system could be pre-trained on common inference tasks, reducing its own computational overhead by more than 60% compared to a generic real-time controller. Light Matter's passage architecture, evaluated against an H100 baseline in a 2023 independent benchmark published through the Hot Chips Symposium, posted a system-level energy efficiency figure more than 100 times higher than the electronic baseline on transformer inference workloads. The lab ran the benchmark a second time before publishing. The number held. Here is the honest picture. Photonic AI chips are not ready to replace electronic GPUs across every workload. The architecture is optimized for inference, the task of running a trained model to generate outputs. It is not optimized for training, which requires high-precision gradient calculations that the analog photonic domain does not currently handle with sufficient accuracy. The gap in training performance between a photonic chip and an H100 is real, and no credible researcher in the field claims otherwise. Manufacturing yield at volume has not been independently verified at the scale TSMC runs for leading electronic chips. The photonic component supply chain, optical modulators, photodetectors, integrated waveguide arrays at chip scale, does not yet exist at the depth required for 100 million unit annual production. And the software stack, the compiler infrastructure, the driver ecosystem, the model optimization tooling required to run existing AI frameworks on photonic hardware is years behind the electronic equivalent. Those are genuine constraints. State them plainly, because they matter for anyone making infrastructure decisions based on this technology. Now here is what the Hot Chips benchmark actually said. Light Matter's passage chip running transformer inference workloads under independent evaluation posted a system-level efficiency of more than 100 trillion operations per watt. The H100 baseline in the same evaluation registered approximately 2 trillion operations per watt. That is a gap of more than 50 times at the system level, accounting for the GPUT, electronic interface, the calibration overhead, and the memory subsystem, not just the photonic compute core in isolation. 50 times. You heard that right. Translate that into data center terms. A 100-rack AI inference cluster running H100s draws approximately 8 megawatts of power, 4 for compute, 4 for cooling. The same inference throughput on a photonic architecture at equivalent system-level efficiency would require less than 2 megawatts total, with cooling overhead reduced to near zero for the compute layer itself. The Uptime Institute estimated in 2023 that cooling alone accounts for between 30 and 40% of total data center operating cost. That cost does not disappear with photonic inference. It shrinks to a rounding error. And this is the number nobody talks about. The International Energy Agency projects that global AI inference electricity demand will exceed 1,000 terawatt-hours annually by 2026. That is roughly 3% of current global electricity production consumed by a single application category, growing at 30% per year. A 50 times efficiency improvement at the inference layer does not just reduce operating costs, it bends the global energy demand curve for the entire AI industry. That is not an incremental chip improvement. That is a change in what building AI infrastructure costs the world. If that number surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover what comes next. The global AI inference market is not a niche. By 2024, cloud providers were collectively running more inference operations per day than there are grains of sand on every beach on Earth, a figure that the IEA's 2023 data center report frames as the fastest growing single category of industrial electricity demand in recorded history. That demand is currently served almost entirely by electronic GPU clusters. Every rack in every hyperscale inference facility is engineered around the same thermal constraint, the one the photonic architecture structurally eliminates. Here is where the consensus broke. When the Hot Chips benchmark results circulated through the engineering teams at major cloud providers in late 2023, the response was not skepticism. It was a procurement question. What does the integration roadmap look like, and what does it require us to change? The answer to that question is what makes adoption genuinely hard and what makes the advantage genuinely durable. Integrating photonic inference hardware into existing data center infrastructure requires more than swapping one accelerator card for another. Server form factors, PCIe interface standards, thermal management assumptions, and power delivery architectures are all built around electronic GPU specifications. A photonic accelerator that eliminates active cooling for its compute layer still sits inside a rack designed around the assumption that everything in it generates significant heat. Retooling that assumption at the infrastructure layer takes years, not quarters. The optical component supply chain, modulators, detectors, waveguide arrays at production volume, does not yet exist at the depth that hyperscale deployment demands. And the compiler and driver stack required to run production AI workloads on photonic hardware is, by every current estimate, 3 to 5 years behind the electronic equivalent in maturity. The part nobody covers is the standards layer. The Optical Internet Working Forum opened a dedicated working group on co-packaged optics integration standards in 2022, specifically addressing the interface specifications that photonic accelerators require to plug into existing server architectures. That working group, which includes engineering representatives from Intel, Broadcom, and every major hyperscaler, is the mechanism by which photonic hardware becomes infrastructure compatible at scale. Standards. Bodies are not exciting. They are where new physics becomes deployable engineering. The historical parallel is NAND flash memory. In 2005, hard disk manufacturers noted that flash storage was too expensive per gigabyte, too limited in write endurance, and incompatible with existing storage interface standards. They were correct on all three counts. By 2015, NAND flash had displaced spinning disk in every laptop, every smartphone, and every high-performance data center storage tier. IDC data shows the transition took roughly 8 years from credible benchmark to dominant market share. The barriers were real. The transition happened anyway. The ceiling that defined AI chip roadmaps for the past decade was not a fundamental limit of computation, it was a thermal constraint. And thermal constraints are an electron problem. What the engineers demonstrated inside that test environment was not a faster chip. It was proof that the material assumption underlying 30 years of processor design, that computation requires electrons and electrons require heat management, is not a physical law. It is an engineering choice, and choices can be changed. The shift from electron to photon at the inference layer does not make AI faster in the way that a new GPU node makes AI faster. It changes the resource equation entirely. Heat stops being a design input. Cooling stops being an infrastructure cost center. The energy curve that the IEA project's bending toward grid-scale consequence by 2026 stops bending in that direction. Not because demand slows, because the physics of serving that demand changed. If you made it this far, you now understand more about photonic AI chip architecture than most people who write about it for a living. Here's what was actually proven. The thermal ceiling is an electron constraint, not a physics constant. The photonic path eliminates it at the inference layer. The manufacturing integration path through CMOS-compatible silicon photonics, co-packaged optics standards, and analog in-memory compute is open and being actively industrialized. The timeline is not settled, the direction is. And here is the part that should sit with you. Every major AI infrastructure build-out happening right now is being engineered around a heat problem that a credible alternative has already solved in the lab. Hundreds of billions of dollars in data center construction, cooling systems, and power delivery infrastructure are being committed today on the assumption that electrons are the only viable compute medium. That assumption is being quietly dismantled in the same research institutions that built it. The engineers working on photonic integration are not building a better version of the existing system. They are building its replacement. One manufacturing process qualification at a time. That pattern, new material, dismissed by the industry that depends on the old one, then deployed at scale faster than anyone projected, is not unique to semiconductors. And if the idea of a material substitution rewriting an entire industry is something you want to understand at a deeper level, the next video is exactly where that story continues. We broke down how a $1 billion glass manufacturing breakthrough is making silicon itself obsolete as a substrate material, and the engineering behind it follows the same logic you just spent 20 minutes learning. That one is worth your time. If this changed how you think about the future of AI hardware, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Do you think photonic AI chips will displace electronic GPUs for inference workloads within the next 10 years? Or does the manufacturing integration gap push that timeline past 2035? Both sides of that argument have serious engineering weight behind them. I read every single one. See you in the next one.